or uniform quantum circuits. So quantum circuits that can be described by some polytime deterministic Turing machine. And so the fact that these two models were kind of equivalent in the sense of defining the functions that can be efficiently computable in the quantum model kind of inspires the work of implicit computational complexity. So the background on this is the work of Bellantoni and Cook that provided a schematic definition of classical polynomial time. So in a sense, a set of functions that have no extrinsic bound in terms of time or computational complexity, but in the rules of how we can construct them, they are sound and complete for polynomial time. And this also in the quantum space also inspired the work of Dall'Ago, Manzini, and Zorzi, and also Yamakami with implicit definitions of quantum polynomial time. So either with quantum lambda calculus or with a function algebra, for instance, with a boundary recursion. And we also did some work on this with a quantum programming language. They also had boundary recursion kind of inspired in the work of Yamakami. And so the usual way that this works is we give an implicit description of so for instance, like a programming language, how we can build these programs, how do they behave, and we kind of show that this is sound and complete for instance, like the quantum Turing machine model running polynomial time. But this can also have interesting applications in terms of circuits. So even though the proof is not directly towards uniform quantum circuits, there are interesting things that we can do about this. And it turns out that, for instance, the link between the implicit description and the uniform quantum circuits is non-trivial. So in 2022, Yuan and Carbon, in their paper trying to describe data structures that work in quantum superposition that are efficient for quantum algorithms, they kind of run into the problem that they call branch sequentialization, which is the fact that kind of in a Turing machine model of algorithms, in the way that we think about it, the quantum control, when it in terms of the branching, we expect the complexity to be the maximum of each of the branches, and that in the end will interfere with each other. Whereas in the circuit model, in a sense, we have to kind of compute one of the branches and then the other in succession. So we're kind of forced to add the time complexities instead of doing the maximum of each. So in their work, they have to restructure their program to do the same thing, but try to avoid this slowdown by using an oscillus, for instance. But they kind of point to this problem that in time complexity, there's this problem. So there's kind of this question of, is there a compilation strategy, for instance, that we could have a set of all polynomial time quantum programs that we know that we can compile them into uniform quantum circuits, and this is kind of to give an idea of how these ideas can be kind of applied into reasoning about circuit complexity. So in our paper with the quantum programming language, we give precisely a way of compiling these things into circuits that are bounded in polynomial size, which is what's indeed not a trivial construction. And so this work is on kind of a new approach, or a kind of a different approach from the previous one in terms of talking about quantum polynomial time. So we start by trying to mix two different lambda calculi. So we start with the dual-affine logic, which was a lambda calculus developed by Péchoux and Terui, where they have types that they that kind of keep track of when we do duplications on, or when duplication has occurred. So for the people who are interested in intuitionist linear logic, so we have here the types, and we have like a linear arrow, and the nonlinear arrow kind of corresponds to the bang on the A, which means that A is a type that we're going to duplicate in the expression in B, and the par A means that the term has had some duplication done to it, and we have the normal polymorphism, and this calculus is polytime strong normalizing, and it's complete for all polynomial time functions. So this is classically. So our idea of trying to give a lambda calculus definition of quantum polynomial time is to kind of take this calculus and try to include quantum operations on it, and to try to obtain like a stronger calculus in the end. And so, for instance, like an example of how this works in terms of bounding to polynomial time. In Delal, the Church integers have this type where we have a nonlinear arrow and we have a par symbol on the right, which means that the term has some duplication on it. And so, for instance, like the integer here is some function that we're going to duplicate. So we're going to have n copies of it. So that's why the par is there. So we can do addition, multiplication, and in a sense, we can, for any polynomial, we can create a term that will have a type which will have a number of pars corresponding to its degree in some sense. And so this is how we can build every polynomial. And it also is kind of safe in the sense where you cannot do anything that's exponential with this calculus, because every time we do some duplication, the par kind of forbids the term from being an endomorphism, so we cannot iterate duplications. So it prevents exponentiation. And so to try to quantize this calculus, you take another one, so developed by Alejandro Díaz-Caro and Otávio Malherbe. And this is a calculus that's very strong in terms of computational operations. So it's sounding complete for single qubit unitary transformations. So I give here like an image of the grammar of these terms and the types. But basically the idea is that we can define booleans and qubits with a sharp representing superposition of some type. And 1 qubit gates, for instance, are from sharp B into sharp B, so superpositions of booleans into superpositions of booleans. And so we have let and match, and we have these ways of building the gate. So for instance, we can build the C0 gate as a let that then matches all of the different possible terms. And then we can type this with a sharp, a pair of booleans into sharp pair of booleans. So two booleans in possibly in superposition into to the same thing. So our idea is to try to mix these two, and we call this the PUNQ programming language. So we have the P for polynomial time. So all the terms are evaluated in polynomial time, and that we want that all quantum polytime functions will have a corresponding term. So we want to be sounding complete. And we also have the fact that we want to be unitary, so quantum also, and all operations are unitary, so we cannot kind of mistreat qubits even in like hidden ways with weird types. And we want that any quantum gate has a corresponding term to it. So the syntax of PUNQ is we have cat 0 and cat 1, we have variables, we have if then else, applications, abstractions, pairs, and the pair destructor. And we have also for any term, so then the sense of this will be, I'll get into it this later, but technically for any term we can build a superposition of terms. So we can, for any possible term, we can consider a linear combination where the coefficients are complex numbers. And so we have also a typing system where we have the booleans, which are the types of 0 and 1. We have linear applications, nonlinear applications, as in Delal. We have pairs and the sharp representing superpositions, the pair to the par symbol to keep track of duplications, and the polymorphism. And so this is the set of rules is kind of a combination of lambda S1 rules that ensure unitarity when we deal with qubits, and we also have Delal rules to make sure that we cannot iterate over polynomial time. The fact that we have so many rules is kind of a result of the fact that we have, for instance, a classical if and a quantum if. We have two different types of arrows, so nonlinear where we can have duplication and linear arrows where we cannot. We have quantum pair, like kind of pair structures that can safely handle superposition, but other ones that are more general when we can only use like booleans, for instance. So we have kind of these different techniques that we can use, which are interesting, but in the end it also looks like a lot of rules, but it means that it's expressive in the sense we can do a lot of stuff. And so in terms of the properties of PUNQ, we can show subject reduction. We can show that for any kind of constant size, at least for any like n entry qubits and k output qubits. So consider like this type here on the right. We are sounding complete for all of these qubit transformations. So in the sense, sounding complete means that we can do any unitary transformation. And also these n and k coefficients have the property where if, for instance, k is larger than n, then the term behaves as an isometry, so it'll preserve in a product. If k is precisely equal to n, then this will be a unitary transformation. And we also have that if k is smaller than n, then this would represent qubit erasure, and in fact it's an uninhabited term in PUNQ, so it's not something we could type. And we do this with a realizability model, so we kind of, for each type, we can talk about like what are the possible terms that would correspond to this type, and we prove that the realizability model is sound for the typing rules, and so we can kind of reason in a simpler way about what terms would correspond to each type. And so in terms of work in progress in this, we don't have yet a quantum polytime completeness, and we'll get into why that's harder than it looks. But first I'll give some examples of typing in PUNQ. So for instance, to say that the plus and minus states are indeed qubits, we first state that the ket0 is a Boolean, the ket1 is a Boolean, and that they are orthogonal. So we have kind of this notion of orthogonality for types. So given a type, we have some definition of what it means for two terms of this type to be orthogonal, which for Booleans and qubits is okay, but if we get into more complicated stuff, it makes the language, kind of undecidable in the sense if we're talking about like orthogonal functions and orthogonal any possible term. But for Booleans and qubits, it's rather simple. And then we just check that the coefficients, that the sum of the squares of the norms equals to 1. And so this says that indeed plus and minus are superpositions of Booleans, or more simply qubits. And so, for instance, to define the Hadamard gate, we can do this. So we can have that the plus and the minus are indeed qubits, they are orthogonal, and then having some qubit variable, we can use it in the if. So the fact that we are using the qubit variable in the guard of the if forces us to check that the plus and the minus are orthogonal. So if indeed we are using just a Boolean value, the two branches could be the same. We wouldn't care. But since the guard of the if is a qubit, we check that it's orthogonal, and then we can just use subtyping to say that a superposition of a Boolean is just a superposition of Booleans. And then we can close the application, and we have the Hadamard gate. So this is kind of how we can construct gates. And so kind of difficulties of the interesting part of this is that we have in PUNQ two different contexts. So we have a linear context in the typing, we have a nonlinear context, as in Delal. Differently from Delal, we don't have a full weakening. We only have weakening on the nonlinear context, because the linear context is where we would want to be strictly linear, because it's where we handle qubits and other types of data types. And so we have linear applications and nonlinear applications, and we have linear abstractions and nonlinear abstractions. So in the linear application, nonlinear application, we can admit at most one free variable in the thing that's going into the application, and this is kind of just to prevent kind of hiding variables inside the term, which is going to be treated non-linearly, and to prevent exponential stuff. So it's kind of more on that regard. So if there's any variable free in the expression going into the nonlinear abstraction, it becomes nonlinear. And then this is interesting because when we close nonlinear variables, we transform the type. So in a sense, we could have some qubit type that was in the context that we treated nonlinearly somehow, and so far so good. It changed sides in the typing context. But once we go and close this and say, okay, now I'm going to define a function based on what I did to this qubit, the typing discipline forces us to say that it's no longer a qubit. So we have a bank function, which is not a modality in this case, just something that transforms types. And so it's something that says Booleans, it's fine to copy. Functions, it's fine to copy. We can treat quantum gates non-linearly. You can copy them as many times as we'd like. And a pair is, we can copy it if we can copy both parts of the pair. And obviously superpositions, we do not allow them to be kind of copied or cloned. So this kind of, we prevent even in the nonlinear arrow to do like stuff that's nonlinear to qubits. And so in kind of mixing these two typing systems, we can do like Del style iteration with the lambda S1 term. So we can have some gate G and we can iterate it a polynomial number of times and to do like a Polytime quantum random walk, for instance. And this works fine with no problem. But kind of the difficulty that that we may have is talking about lists of qubits. So lists in Del or polymorphism. So for instance, like a list of booleans will be will have this type. And to reason about lists of qubits or superpositions of lists of qubits is very tricky, because now we have to say what does it mean for two lists to be orthogonal. So given the type of the list, given a polymorphism, we have to start thinking about orthogonality of polymorphism and orthogonality of functions. And this was kind of the first direction we were going until we saw that this is actually kind of hard to think, because kind of the first approach was, okay, two lists will be orthogonal, so having this type if for any type that I give to them, or any closed type or polymorphism free type, then they'll like inductively satisfy the orthogonality condition for the new like type that I give now that I've given X. But then we have to reason about orthogonality of functions, and then that's very. So we also had the idea of superposing functions, and then we saw that that was indeed very restrictive. So for instance, like if we have two unitaries of the same dimension, for them to be kind of orthogonal, we would like for them to have orthogonal outputs on given the same input. So if you have a superposition of f and g, if we give 0 to the superposition of f plus g, we want f of 0 plus f of g to be a safe kind of superposition in the end, and so they have to be orthogonal. And this is very restrictive, so there are no two kind of unitary gates that would satisfy this. But if we start talking about isometries, then it's okay. But it's a bit tricky, and then we don't know like how much expressivity would have in the end. So this is kind of the roadblock so far. But yeah, so yeah, I'm happy to talk more about any of these things. I kind of went quickly, but if you have any questions, I mean, we have this version on the archive that we're still working on a new version, but I'm happy to take questions.
Yeah, I have a question. Could you go back to, you had a results slide, I guess it was about halfway through.
Yeah. Yeah.
Yeah, that one. So the completeness up there is a different kind of thing from the completeness.
Yeah.
Right? Could you explain?
Yeah, the difference. Yeah, so in a sense, if we consider any kind of fixed dimension unitary transformation, so something that we can, so it's something that we can just create a term that satisfies it. That's easy to do, easy enough. Quantum polytime completeness, we would like, for instance, to have some list or a function that would take some list of qubits of arbitrary size, and that would be able to iterate over the list and to do like operations, so not having any fixed size entry in the term. So in a sense, okay, for any arbitrary dimension, we can define any quantum gate of that dimension in terms of having just some input and to be able to iterate over it and have a general term for that. It requires using lists, for instance, and it's tricky to think about superpositions of lists given the Del types. Okay,
so this first completeness, it's kind of like a fixed parameter thing. If I fix a parameter, then I can sort of two syntactic things are sort of equal if and only if the unitary is the same. Is that?
Yeah, it's the soundness and completeness here. So more precisely, it means that given this type, so between but from n qubits to k qubits, for any isometry, we have a term of this type that behaves like the isometry, in the sense where we give it the input and it'll reduce to the correct output. And any term of this type behaves kind of like this. So if it has the dimensions to behave like an isometry, it will. It has the dimensions to be a unitary gate, it will behave like a unitary gate. And if it's doing kind of qubit erasure, then there's no term that will satisfy it. Yeah.
probably have a better question.
So you had a slide on linearity on this Bang operator you had, and you said that's not a modality, that's a function from type to type.
Yeah.
And I'm just trying to figure out where on this, so are there certain things you can't apply it to, or like, you're showing that Bang AROB is just AROB. Where does this sort of preclude copying?
So it means that like when we're going to apply this rule, we're going to close the nonlinear abstraction. The fact that x of a is on the left context kind of means, like, for instance, like it came from a weakening, and so it doesn't even appear in the term. And so so we have no limit here on the type that can be added. So in a sense, we could add some x of type qubit that doesn't appear in the term. So when we go to close it, the fact that we're performing this, like applying this function to the type, will say that indeed, like, in fact, in the end, this function lambda x t will not be able to be applied to qubits because we'll have erased the superposition in a sense.
I see, and this is the only place the Bang appears in this rule.
in the typing, So it appears here, and it's the only place we use it.
Okay, thank you.
So you showed some type formers that you build unitaries out of if, like branching on ones. Is that the only way you've got to make concrete unitaries, like a particular matrix that I wanted to make?
I think yes. I mean, you can do a lot of complicated syntactical stuff, but I think in terms of like how you would think of a unitary and how you would build it, I think if is the only like direct way of doing it. It's kind of, you think of the matrix and then you just try to write it in these terms. So you kind of think of the columns of the matrix of the unitary you're considering, that those will be the branches, I think.
Yeah. Okay. Thanks.
But then, like for instance, like the controlled version of this, you can like use Adamar. There's like a sub part of the term. Could be like if the first qubit is 1, then the rest of the state will be the Hadamard applied to the variable that represents the rest, and you'll use like a let where the true variables have different dimension. I think it works. Yeah.
Okay. Thank you.
Thank you.